again. Welcome to the next session on our international track. And again, we're talking a little bit about the heating side here. And I have now here with me Daniel Muschick. He's a scientific researcher at Bioenergy and Sustainable Technologies in Graz, Austria, where he specializes in automation, control system, and optimization-based energy management for hybrid energy systems. His work focuses on modeling, simulation, control of thermal energy networks, and I think that's the topic today that he's going to talk about, including district heating systems and renewable integrated infrastructure. He has contributed extensively to the development of mixed integer linearized-based energy management frameworks and advanced control strategies for complex multi-energy systems. He holds a PhD in control engineering and also a master's degree in telematics. He has published a lot in leading journals, and I don't want to say too much now because we're on a tight schedule. So Daniel, please hack it away and talk a little bit about your research here. Thank you.
Thank you very much, Michael. Thank you for the opportunity here, and thank you to everyone listening. So I'm going to talk a little bit about, again, heat from an Austrian perspective, if you want, even though I think it's also a global perspective. Just a very short introduction on my side. So my name is Daniel Muschick, as Michael has nicely pointed out. So I'm from an Austrian research organization, like the previous speaker. I'm from Austria. This is not Australia. It's the small country in Europe. We are called BEST, Bioenergy and Sustainable Technologies, GmbH. And we are an extra university research organization, mostly focused or stemming from the research on biomass combustion conversion and gasification, but more and more going into the system, looking at the system perspective and looking at the systems, the energy systems in general, also including now electricity and not only biomass and then heat, where we came from, but also electricity. And inside of this organization, we have an area that's mainly focused on automation and control, and that's where I live and breathe and research in. So it's really about getting the best out of individual technologies, but also, and that's my part, getting the best out of systems of multiple technologies. My main focus here today is why we should use heat for flexibility, and Austria, as I said, is more or less a byproduct. We can first talk about the incentives. I think those are more or less clear. So we have more and more increasing variable tariffs and price signals on the electricity side. So my comparison to the US is, I'm not an expert on the US, but just giving you a brief idea. So in the US, you have mostly time of use pricing, and you have those demand charges, which means that you pay for very high power uptakes. If you have a short power peak, you pay more, for example. And in Austria and in the European Union, there's a strong new drive towards dynamic tariffs, because we have also established lots of smart meters. So there was a smart meter rollout in Austria, which means that almost every single household now has a smart meter with a quarter-hour resolution. And this means that even personal people, so individual households, can now have a tariff that's really on an hourly basis, having a different price for the electricity. And this also allows what the previous speaker has talked about, these energy communities, which essentially are just a balancing scheme where you can work together with friends or in your community and exchange the electricity between you. And this is only a balancing scheme. So it really looks at how much energy did you import, how much electricity did you export in 1 quarter hour, and then you only pay for what you didn't get from the community. You have to pay to the utility. And so this is very, very coming up in Austria and in the European Union itself. And now the big thing that I'm talking about is heat. And so the question is, how does heat come into play when we talk about main electricity? And that's, of course, because of the sector coupling that the previous speaker also talked about, in this case, heat pumps. They are very, very much coming in Austria. So we have lots more of heating demand than you have in the US. Cooling demand is coming up. It's much less established as in the US, but it's coming. And we have lots of photovoltaic installations. It's even mandatory for some buildings and in some states in Austria to have PV installations on your roof. And so it's very logical to also include heat pumps for heating your building. And here another specialty of Austria comes into play, which is that our building stock is very much different from the US. So we have a much more thick building envelope. We have much more insulation in our existing buildings, but especially in our newer buildings, they all have to comply with some standards and regulations. So it is possible to use these buildings as a storage for heat and through the heat pump also for electricity. Just to give a very brief overview of what this means. So typically, if you have a single family home, you might have a capacity of you might have PV plus battery, and this battery might have 5 to 15 kilowatt hours of capacity. And if you look at the heating sector, even with a rather small storage of 1,000 liters and only a temperature spread of 10 Kelvin, so 45 to 55 degrees Celsius, this already is more or less of the same capacity as a big battery, only for very small thermal storage. And so we have this capacity, and it's mostly available anyway. So if you build a home, you install a heat pump, you will have a heat storage, and you can make it bigger if you want. And the price difference is it's almost or even more in some cases than the tenfold. So it costs a tenth of the price to have the same capacity for heat than for electricity. Of course, you have to be a bit more honest here, because storing heat is not the same as storing electricity. If your heat pump has a coefficient of performance of 4, you only have a fourth of this capacity available as capacity for electricity. But still, it means that there's a substantial amount of capacity is there to shift electrical demand. So it's much more affordable. And there's also something else that comes into play, which is that we have this building mass available. We have, as I said, well-insulated homes with a higher thermal mass. That means we can use the building itself as a storage. The problem with this is that heat is also a little bit more complicated, and that's where my research comes into play. Heat comes in different flavors. You have different temperature levels. And especially if you think about using the entire building as a storage, it's not as easy as that, because, of course, how you operate your system influences how much capacity you have. You can't just heat up a building and then leave it at that. The building will cool down again. People will get uncomfortable. So it's getting a little bit more complicated. In order to use all of this flexibility, we need some kind of predictive framework that can take this complexity into account. And so this is what we are developing at BEST. So we're trying to tackle some challenges with our solutions. So one of the challenges that we see is that we want to have optimal operation, not just any operation. So we are focused on optimization-based approaches using mathematical optimization. We have the big problem that many things here in this case for using flexibility are volatile. So the yield from photovoltaics, the heat demand, the power demand, everything is volatile. In our cases, with these spot market prices, it's even the spot market prices which are not constant. They vary every time. It's different from the last. So we need some kind of system that is predictive and can tackle these challenges. And even more than in the electrical side, we have a very high range of variations in our systems. Which kind of buffer is installed? How is domestic hot water produced? Is it from the storage itself? Is an additional storage installed, and so on and so on? Which components are there to produce heat? A boiler, a heat pump, a heating rod. So whatever the solution to this problem is, it needs to be modular and allowed to automatically adapt to different setups. And so this is what we develop. It's a supervisory control framework based on model predictive control, where the input is a specification of what components are there and how they interact, information about future tariffs or predictions of future tariffs, a weather forecast that we query from weather services, and then from this derive forecasts of our own, predictions of electricity demand, heat demand, solar yield, and so on. And then we provide set points to individual components, to the heat pump, whether it should switch on or off, at which power level it should run, whether a boiler should switch on and off, and so on. And these set points are then executed, and we are re-optimizing the entire system in an iterative manner. This is something that you've probably heard of a lot, because many people are using this and doing this. What sets us a little bit apart, what I think is more or less our unique selling point, is that we really consider heat with all its facets, with the temperature levels. So if you use a conventional energy management system or some kind of optimization-based system, it thinks about energy as something that you can just add and subtract. So whatever the solar collector delivers, the heat pump converts to heat. So this is a PV heat pump. You have heat, and that's the demand. But in reality, it's much more complicated because the heat pump has a different coefficient of performance depending on the temperature levels you operate it at, depending on the ambient temperatures. The capacity that you have for storing heat is largely depending on the temperature spread. So if you heat up the water from 30 to 50 degrees, you have twice the capacity than if you only heat it up from 30 to 40 degrees. But if you go to higher temperatures, the COP of your heat pump is lower, and so on and so on. So if you just use an energy-based optimization, all of these aspects are lost. And our approach uses a multi-temperature optimization. It's still, from the technical ones among you, it's still mixed integer linear programming based. There's a link, a reference to the publication here, but it can tackle all of these challenges. So the big advantage of this modularity is that we can use the same framework, the same optimization framework for multiple applications. And we have, for example, single family homes. We have a product out there where we provided our framework as a service to a company which now sells it together with the heating appliances. We are currently working on energy communities, really EV charging and so on. Solar thermal processes we did in simulations. Office buildings, I will show in the next slide. We've already implemented something there. For district heating, we've did some implementations on a large scale, and for business and industry as well. So how does this look like for an office building? This is the building, at least a sketch of the building I actually work in and sitting right now. We developed a predictive software that controls the heating in this building. Depending on user feedback, people can say whether it's too hot or too cold, whether they're comfortable or not. And based on, as I said, weather forecasts. And just by using our predictive system that has a mathematical model of how the building reacts, we were able to, at the same time, increase comfort. So reducing the time the people were at uncomfortable temperature ranges and increasing wet and comfortable temperature ranges. So comfort increase, and at the same time, energy increase, which normally is contradictive. But in this case, it's a building with thermally activated building components. It's a slow system to react to changes. And if you don't have a predictive component in it, you typically operate it in an incorrect manner, and people start to open the windows and heat in summer and they cool in winter because they are so uncomfortable. What we also tried to do is to actually use now the building mass as a flexibility, as I said before, for the electricity sector. And this would be the power uptake of the building depending on different electricity price scenarios. So we have one thing which is orange at the top and orange at the bottom, which would be a constant tariff, where the electricity uptake would look like this orange curve. And if you had a different time varying price, like in the green curve below, you would get the blue uptake of electricity. So in essence, the main message is clear. We can use the building as a flexibility, but, and this is also something I want to emphasize, it's not as clear cut as it looks. We can't just say this building has a capacity of so and so many kilowatt hours or megawatt hours. It really depends on how you operate it and what the temperature comfort bandwidth that you can use is. So it really depends on the time of the year and so on. So it's very complicated if you can't use mathematical optimization to run it. Simple rules don't really use up the full potential. We also use this framework to do some scenario analysis and some design on systems that rely a lot on heat. I will go quickly over this because I just want to show how complicated things in the heat sector can be. So this is a thermal bath where we have a splash basin that we can use as a waste heat. So it needs to be cleaned. The waste heat from this cleaning can be used for a heat pump. They have a large PV installation on the roof that would largely exceed their current demand. So we have surplus electricity at their disposal. We have some kind of waste heat from selling water that we pump out of the ground. But it gets very complicated. So we have temperature available at different temperature levels. We have thermal energy storages for cooling, for heating. We have heating demand from hotels surrounding the spa, which is completely different from the heating demand that the heating network that's also connected requires. And the big question now for the operator of this was, we have gas boilers currently, but we want to change to something more renewable. How could we move this to renewable energy sources? So how could we use heat pumps to solve this problem? So which kind of heat pumps do we want? Do we want one big one, larger, multiple smaller ones that are more flexible maybe? How large should the storage be, and so on? So lots of design questions that are very difficult to answer if you only look at energy and not at what the temperature influence also, what the influence of temperature is on the result. And just as an image of how complicated it can be, so this is more or less the BNDD schema where you see what the components are and how they interchange heat. And this is then our representation in our optimization framework, where all of this energy and flows and the temperature levels are considered. So I see that it's not trivial anymore, because everything has to be handled individually. But in the end, we were able to explore multiple scenarios. So it's not an optimization-based design as with Xandy maybe. It's really, okay, what if we use this kind of storage, what this kind of storage, how would it differ, how much would it cost? So we really make yearly simulations based on this, and then decide which one of the configurations is the best one. And this would be the results in this specific case, that you should rather use multiple smaller heat pumps so you're more flexible in how you operate it. But in essence, the framework allows to do this also to provide design decisions. And this brings me to my conclusions. So there are large market incentives, both in the USA, also in Austria, all over Europe, based on fluctuating tariffs, even more so in Austria with these really time-depending tariffs. But we have at our disposal flexible buildings or storage in industry. So it's not really limited to this, but this can scale to large quantities. And if you are able to predictively use your heat, so if you can look a little bit into the future and do the right thing, you won't be making the occupants of your building uncomfortable, and you will get the best out of your system. But you need a little bit of intelligence to do so, and only looking at energy, in my opinion at least, is not sufficient. You need to look at different temperature levels. That's my conclusion for today, and I'm looking forward to questions. Thank you.
Thank you, Daniel. And I know for a fact that this is really great research. So thanks for talking about this. There are a couple of questions which are maybe not directly related to your controller. And I have a couple of questions, but let's start here with a generic question from Greg. What's the best building material?
That's an interesting question. Yeah, what's the best building material to use in a building?
I need to repeat this for everyone else.
Yeah, sure, sorry.
What is the best building material to use in the building to provide mass for optimizing heat retention? Can autoclaved aerated concrete serve this role? I even don't know this material, so maybe you know about this. I don't know.
No, I'm in a task for using heat, so buildings as storage, but I'm not an expert on material. I think one of the main challenges here is that you have two kinds of interests that are competing. On the one hand, you want to have the most capacity. So I think aerated doesn't look like, or doesn't sound like it has a lot of capacity, but it has a large low conductance, so high insulation probably. So this would have high retention, but what I would prefer probably is to have a concrete slab and then some insulation on the outside, that if you really want to keep the cool down slope. But I'm not an expert on that.
To add on this, the walls, as you said, are pretty thick in Europe because it can be really cold. I mean, we're talking here about walls with 50 to 60 centimeters. So we are talking about almost 2-foot walls here. So there's a lot of mass. And I think that's the main difference, because in the United States, I mean, all the buildings, at least the residential buildings, are built out of wood, which has very little heat capacity. So the other question, is the stratification, the buffer tank stable? How do you avoid or address layer mixing?
That's also an interesting question. So no, they are not. It depends. For heat pumps, normally they are not, because heat pumps typically have a smaller storage. If you build a larger one, then it's much more stable. But mostly if you think about boilers, biomass boilers are very common in Austria. There you have a very good stratification. For heat pumps, more or less the circular admit with a much higher mass flow, so it's not that stable. What we use, for example, for solar thermal are stratification lenses, where we really try to insert the water at the right height, so it doesn't mix up too much. But in essence, this is a very valid point. This could mess up things a lot. But yeah.
So the last
really
question is interesting, and we have to think about this. Is there model integration of thermal optimization energy costs, perhaps with Xendi? So maybe you want to take a step on the first step on this one.
So I think this is about the design, right? Because So I know about our colleagues in Austria that extended on their cam here with a little bit of heat. I'm not sure how far Xendi considers this, but I guess you can have different temperature levels at least. So this is definitely a point. I think where it becomes very complicated, especially if you want to have optimized design, if you really want to think about stratification, if you really want to think about different efficiencies at different temperatures that appear at different times of the year. I'm not sure whether this is really suitable for a global optimization of the design and the operation and everything at the same time, but it would be a very interesting question. I haven't tackled it yet. We do mostly scenario-based analysis.
Daniel gave a great answer on this, and we have a history working together at some point, and we did some tests around this, right? And heat up processes, for example, what is the impact of heating up the system, right? And Daniel already alluded to this. If you want to have a tool which can be used by most people by themselves, you need to probably take out some of the complexity, because what Daniel is doing is in a lab setup, and I'm pretty sure there are a lot of people in the background helping him to do this project, right? So it's cutting edge research. At the end of the day, the question becomes how much is it really impacting the overall design, as Daniel was alluding to this. And I know, as I was still working on some of this research, we did some analysis, and there can be an impact of preheating by 5 to 10%, right? So the question becomes, a 5 or 10% improved quality really impacting a model which you do for 20 years, right? So, and if I understand you correctly, Daniel, you have a mix here between simulation of the operation and design, and you go back and forth. In this way, you get way better precision here, right?
Exactly. So there are things where we very simplify everything down, where we have a large consumer base, which is this one consumer commercial product that we already produce, but it's very limited in the configuration that it can handle. But for those, it works well, and then you can deploy it. But as soon as it gets very specialized, I agree with you, it's not something every person in the world can just use and get the results he wants. Mm.
So I have a final question here. I mean, we're talking a lot about Austria, and I just want to make this a little bit more appealing for the audience here for other countries. So, I mean, do you see a potential that this heating and controls can play a role, I mean, at least in Europe on a larger scale, or maybe also on the East Coast of the United States? I mean, I'm not sure if you have, because I know that you guys have collaborations going on with the United States when it comes to biomass, but I'm not sure if you're thinking about doing something maybe on the East Coast, and maybe that's also something that could come out of this, that maybe people are interested in this if it's about heating on the East Coast in the United States.
I think this might be very interesting. I think you have a lot of cooling demand, which is also something which could be used in the same way. Typically, you have a different temperature spread, so the capacities are slower. But sure. So as long as there's some kind of flexibility available, either through storage or for building mass, but also, of course, always in the industry sector where you always need process heat. So we have, as I said, with solar thermal, that they build large-scale solar thermal systems to provide process heat for the milk industry, for example. I guess many applications also exist on the East, on the West, and everywhere in America, actually.
And actually, I think you could easily apply this also to cooling, because, I mean, there's no difference.
Exactly.
Heating. So I think with this, I want to really close this interesting presentation and also conversation. Again, so that you know, we have to close this room, and in 5 minutes, we have a panel discussion which talks a little bit more about the energy communities, the resilience in Europe. So just see you in 5 minutes there. And thanks everyone for attending this, and thank you, Daniel, for presenting here.
Thank you very much. See you.